In this video, we are going to talk about 3D scanning and fixtures. Specifically, we're going to talk about how 3D scanning can be used in conjunction with fixtures, can be used to inspect fixtures, and sometimes can be used to replace fixtures, as well as doing fixture design. So what we'll cover specifically is what is a fixture, the applications fixtures are used for, why people use fixtures, and then how 3D scanning and probing can be used in many of these processes. And we'll kind of use 3D scanning and probing interchangeably, and you'll see more about that in the video. Sometimes it makes sense to do scanning, sometimes it makes sense to do probing. And we're going to go through 5 real-world examples of different applications and where 3D scanning is beneficial. So let's start by talking about what is a fixture. And in its basic definition, a fixture is just basically a tool to hold a part or parts in a defined position. And typical parts that are fixtured are things like sheet metal parts and plastic parts. Your bigger, maybe rigid machine parts may or may not require fixturing. We'll get into more of that later. And fixtures can be temporary, where you put together some components to fixture something up on kind of a temporary basis, or it can be fixed, where you're building a dedicated fixture for a specific part. They're all also often referred to as tools, gauges, jigs, fixtures. All those words are kind of interchangeable. A little bit has to do with what is it you're trying to do with the fixture and what terms are typically used. But they are used for many different applications. So specifically, what are fixtures used for? Well, holding is one of the big ones. And holding just means that you're holding the part in a position so that you can do inspection, machining, welding, maybe some kind of assembly. But it's also used as a gauge to actually hold the part and then measure using gauge pins, gauge block, different things like that. It can be also used to locate a part in a certain position, maybe for other applications. And then, of course, it can be used to do measuring or verification and measurement. And this could be just a part that has to fit inside a fixture to make sure it's the correct size. It could be something very simple. So those are some of the main applications that fixtures are used for. So why use a fixture? Well, again, the primary reason is to hold a part or a series of parts in a certain shape or orientation so that then some other operation can happen. They're used a lot to make sure a part is correct. So it's used for inspection. So you want to maybe hold the part in a certain orientation, a certain position so it can be inspected. They offer repeatable results. If you could hold the part the same way every time, then whether you're doing assembly or welding or machining, you should get repeatable results. If you have a good fixture, you should get repeatable results. And they're typically used for volume applications. Fixtures can be complex and expensive, so if you're only doing a couple of parts, you're probably not going to build a big, expensive, dedicated fixture. But if you are doing volume, they are very efficient. Typically, they can be easy to use. It depends on their complexity, but most fixtures, a typical operator can locate the part into a fixture, and then it's usually either manually clamped or automatically clamped, or air or suction or even magnetic force will hold it in place. And many fixtures can be configurable, so they may work with many parts, and it gives them a lot of versatility. So how does 3D scanning and probing fit into this? Well, 3D scanning or probing, and again, we'll use those words interchangeably, and that could be anything from a CMM like you see here to more of a shop floor probing system, which you'll see in a little bit, and then also 3D scanning. They can be used to replace many fixtures. A lot of parts can be inspected or measured without a fixture. Typically, those are going to be rigid parts. Part of the reason you need a fixture is to hold a part in a certain shape, and if that part is very thin or can move around, a fixture is probably needed. But many parts are rigid, and traditionally they might be fixtured up in a certain way, but with a lot of this newer technology out there, we don't need fixtures for a lot of parts as long as they're rigid. But we can also do virtual flush, gap, location, and other checks that traditionally were done with hand measurements. We're going to go into that a little more in one of the examples. But a lot of these checks that people typically did by hand can now be done virtually. 3D scanning and probing also helps to validate a fixture. Before you can start using a fixture, you need to know that fixture is correct. If there's nests or certain areas that a part has to sit on and then it gets clamped down, you want to make sure those are right. Otherwise, they may deform the part or put it in a position that is not correct. And again, we're going to go into more detail. And 3D scanning and probing can be used in conjunction with a fixture. You may still need to hold the part in the right location, but then from there you could do scanning instead of maybe traditional hand checks, and we'll cover that. Some of the advantages of 3D scanning and probing is they can capture typically much more data than manual checks where you're just checking maybe a whole location with a pin or a gap check or something like that. If you're 3D scanning it, you can collect millions of data points that you can use. And it typically, or many times, can be faster and more repeatable if you're doing scanning or probing. And then in addition, with all that data you're capturing, that can be used in downstream SPS and other software applications where you can look at trends and look at statistics. So maybe over a time, a part is not in compliance anymore. You can go back and look at that data and maybe start to see trends as to what is happening. Maybe a whole location is shifting over time. You may go back and look at the tool and maybe be able to determine something. All right, so let's get into some real-world examples, and we're going to show you more in depth here some of the things you can do. And the first one we're going to look at is this is a holding fixture for welding. So an automotive series of parts, it gets placed in this fixture, it gets clamped down, and then spot welding goes on. So the first thing that has to be done is these fixtures need to be validated, because if they're not validated, the part may not be held in the correct position, and then when you go and weld them together, a series of parts, you may go assemble it in the car and it doesn't fit right. So you've got to make sure your fixture is correct to begin with. And then you have to continually check the fixture, because over time, this thing gets a lot of wear and tear and big heavy parts and a big spot welder and heat and everything is going on. And, some of the stuff is adjustable on the fixture and it can basically get, moved over time. So you many times have to make adjustments to these fixtures and then recertify them. Also parts, locator pins, pads, different things, nests on these can wear out over time. If it's a heavy use and it's metal on metal, you can get some wear. So in this case, we're going to go into more detail on how this whole process was done. Okay, so let's go ahead and take a closer look at the fixture, and we'll start by looking at the actual CAD model that you see here. It just can be a little bit easier to visualize what's going on. But basically what you have is multiple sheet metal parts that are basically clamped and held in car body position so that then a robotic spot welder can come in and spot weld in numerous locations to basically hold all these parts together. And what we're going to need to do is go through and inspect this fixture and make sure that all these holding points are correct so that the parts don't get held in an incorrect position, because once they're welded together, there's basically no turning back. So let's go ahead and take a look at the actual fixture. And as you can see here, there's a lot going on. There's a lot of moving pieces and clamps and pins, locator pads, etc. But this is what a typical welding fixture would look like. So to get started, the first step in the process is to set up a coordinate system to start doing the inspection. And typically a fixture is going to have tooling spheres, pads, holes, some way of positioning a coordinate system or a datum system, and that could be in a world coordinate system. Typically for automotive, they use a Cartesian coordinate system, but you need to set that up. And to do that, we're going around on the fixture and probing these key points as they're called out in the drawing, so that then all of our measurements are related to that coordinate or datum system. Now, once we've established our coordinate system, now we're going to go in and 3D scan the fixture. And we're only going to scan it where we need to. Basically, anywhere that the part nests or touches the fixture, any locating locations, locating pins, holes, whatever it may be, we're going to scan all of those areas so we can compare them back to the CAD model to make sure it is correct. So now what we can do is overlay the scan data on the fixture, and that should automatically come in the right orientation because, again, we've established that coordinate system. And you can see here we've color-coded the scan data with a tolerance, and this is just a quick visual check, but we'll go into all those key locations and pull actual dimensional measurements or do GD&T and make sure that this fixture is correct in the way it's holding the part. And if it's not, it can, depending on the fixture, it can be adjusted, or maybe some pads or nests need to be remachined. But typically they can adjust it so that we can get this fixture to hold the part in the correct position for the welding operation. So let's go ahead and take a quick look at the inspection report. Again, here's kind of an overlay of that scan data. But more specifically, we're going in and measuring key nesting or location points and calling out their measurements. And you can see in this case there's a failure over here where it has to hold the part. We've got some interference there as well. Over here it passes. So we can go through and measure all of these critical location and nest areas and make sure they are correct. And again, if they're not correct, we can do some adjustments. Most fixtures are designed that way to get them into the correct position. Now let's take a look at a different type of fixture. And this is a checking fixture typically used to check gap and flush checks. This is very common in the automotive industry for exterior body panels or on the interior, some of the trim pieces. But what this fixture does is two things. It looks at the gap. So you have, in this case, a truck grill sitting in the fixture. And then the kind of brown tan area of the fixture, that represents the surfaces that match up to it on the vehicle itself. So the hood and maybe the fender coming around the side there. So you place the part on this fixture, and then there's on these little chains or pins that you slide in there to measure that gap. So you see that gap on that panel. You want that to be consistent all the way around. So if that pin doesn't fit in, the gap would be too small, and if there was play or slop in there, it would be too big. And then they also do a flush check, and flush is where the one panel kind of then transitions over that gap to the next panel. You want that to be kind of smooth or flush. You wouldn't want to run your hand over there and then kind of hit the other panel because it's raised or maybe it's low. You want that to be nice and smooth, assuming that's the design intent. And they'll use a dial indicator or sometimes another pin to kind of check, or a tool to check that flush check. But fixtures like this are very expensive to build. They're complicated. They take a long time to make. A fixture like this easily could take months to get, and they're expensive. And then all your measurement is then done manually. So how are you reporting this? Are you just measuring it and There can be some, depending on the user, you may get different results. Are you just recording this manually? So great effort goes into building this fixture, but then all the checking is done manually. So we're going to show in this example how 3D scanning can be a real benefit to a fixture like this. So if we go ahead and look at the CAD data of the grill, and then we have the panels basically around the grill, you can clearly see in the design where that gap is. And then the other panels there, you can see where they are flush. So if we have all of this data electronically, why can't we do these checks electronically or virtually? We don't necessarily need that fixture to do those checks. Now, one key thing though is we do need to hold the part in the correct position, in the assembled position, because the part is plastic, it's thin, it's actually an assembly of plastic parts, so you would still need a simple holding fixture to hold the part in the correct position. But from there, we can just 3D scan the part and then do the flush and gap check virtually to the panels around it, because we have all of this stuff in 3D CAD. To do these measurements manually, in this case we're going to use Polyworks inspection software, and we basically define the gap. We do some things to kind of define the direction and location, and then we can go in and measure that gap distance anywhere along the part and pull out locations, or pull out that gap distance. So we can measure millions of data points all the way around this gap and put them in a report like you see here, and look at where there could be some issues. And again, we're doing this all virtually. Now for flush, it's the same thing. We can go in and define it and then cut sections through the data and look to see if the panels are flush. And Polyworks has specific flush and gap reporting tools to put this information in a way that can be understood by engineers or metrologists and analyze it. And again, we're doing this on unlimited amount of points and data, so you can really get hard data that you can compile into different software or a spreadsheet or something like that. So you're going to get very, very accurate data. You're going to do it all virtually. You still need to, again, hold the part. You're going to need some kind of holding fixture to hold the part in the proper location, but you do not need to do those manual checks with pins and gauges and all that. It all can be done virtually. You'll have a lot more data that you'll be able to work with, and assuming your scanner is accurate, you'll have very accurate and repeatable results. In our third example, we're going to look at a complex fixture, and you can actually see there's two fixtures here because we're checking the part both from the top and the bottom. So the part is placed in the fixture one side. You see all the little white blocks. Those are bolted into place to hold the part down in the fixture in the correct part position, and then it's inspected. So it's done on the one side and then taken out, flipped over, and put into the fixture for the other side. So the first step in this operation is we need to inspect the fixture and qualify the fixture itself. And it does have, a few areas that do have some complexity involved with some CNC machining to get the part to nest correctly. But this part is a very thin interior trim piece. And we also want to be able to inspect the part not in the fixture. So we want to scan the part not in the fixture and then also in the fixture and look at the differences, because it can be a real challenge with sheet metal parts and thin injection molded parts to hold the correct shape. So when the part comes out of the mold, because of shrinkage and just other things involved in the manufacturing process, the part can actually not be in the correct position. Now, a little bit of that is okay, but if you get too much where you have to really flex or bend or change the part to get it to even fit in the fixture and go back to part position, there can be some issues there. So we're going to qualify this fixture, but we're also going to inspect the part both in the fixture and out of the fixture, and look at it. In this animation, the red part was scanned in the fixture and the blue part was scanned out of the fixture. And when you line the two data sets up, you can see, especially up in these areas, there is a gap between the two parts. So that needs to be studied and analyzed and make sure, that's not too drastic of a movement when we place that in the fixture, and we're not deforming the part too much. Like we did before, we will use probing to qualify the fixture, basically going around and measuring the fixture at key nesting and hole locations and make sure our fixture is correct before we start inspecting parts. Because if your fixture isn't right, there's no way to guarantee that then your parts are right. So the first step is always qualifying that fixture and making sure it was built right. And probing is very quick and easy to do this qualification process. Once the fixture is validated, we can now place the part in the fixture, clamp it down, and that's going to hold that part in the correct position. So this is a case where a fixture would absolutely be required to hold the part in the correct assembled position in the vehicle. And then from here, we're going to use either probing or 3D scanning to inspect the fixture. And it can be a combination of both. Sometimes for like small holes or parts that have like thin edges, probing is a really good way to go because you can actually make contact with that probe either down in the hole, or you use a probe tip that's big enough to kind of sit in the hole a little bit to find the center of the hole. And then again, for edges and other thin features or down inside thin cavities, probing is a good way to go because you can make that contact. But again, it can be used typically in conjunction with 3D scanning. So we'll go around now and 3D scan this entire part in this fixture position, and then we'll compare it back to the CAD model, which is also in that correct fixture position, true car position, and we'll run our inspection reports and see how accurate our parts are. But again, this is a case where you absolutely have to have a fixture because of the distortion of the part coming out of the mold. And this is not uncommon in thin-walled, injection molded, and sheet metal type parts, just because of the way the manufacturing process works. In plastic parts, it shrink. In metal parts, you can get spring back. You can get different things. And so that's why you absolutely have to fixture those parts so you know that they are correct. For our next example, we're going to show using 3D scanning for fixture design. What you see here is a very simple holding fixture, and what we have is a sheet metal part. And what can often happen in the sheet metal process is it doesn't always match the CAD perfectly. And that's because the sheet metal process can be quite complex. You've got the initial forming, you may have some piercing or cutting. There's a lot of different trimming, shearing, folding. There's a lot of things that can go on in a sheet metal stamping process because many times it's multiple steps to get the part formed the way you want. But you can kind of notice on this part here, you can see some wrinkles along the edge, and those are not in the CAD model. So if we're trying to build a holding fixture and we want it to have a very good fit, even if we have the CAD may not match this sheet metal part perfectly. The other scenario is maybe there just isn't CAD available. Maybe you're buying these parts and then mounting something onto it or changing it in some way, and you just need a simple fixture to hold it. So what we're doing here and what we're going to show is we're going to show you how to build these nests so they fit perfectly to the part, basically where they're holding the part, plus the blocks that hold the clamp. And we're going to show you how you can design those with 3D scan data. And these are just simple 3D printed blocks that we use for this fixture. And that's becoming quite common, is people are using 3D printing. So we're going to walk you through this process. So starting with the 3D scanning, on a part like this, it literally takes a matter of seconds to a few minutes. Very easy part to scan, a very open, clean geometry. So we can quickly 3D scan either one side or both sides of this part in, again, just a matter of minutes. In this case, we're using a handheld laser-based handy scan scanner, and you can see just how quickly we can scan this. And we'll go around, make sure we get it good, flip the part over, scan the other side, put those two sets of data together, and then we're really ready to start our fixture design. All right, next we're here in some reverse engineering software, but this potentially could be done in a CAD system depending on your system's capabilities. But what you see here in silver is the 3D scan data. Now this is just a mesh. So if you come in here and turn on the edges, you can see it's just scan data. It's just a mesh. It is not a CAD model. But we've already started to design the fixture like you see here. But let's go ahead and build one of these nesting blocks. And as you can see, it may be a little hard to see. You can see all the wrinkles in the sheet metal here, which is again pretty typical. You can really see it here. You can see the kind of the rough edge. And we're going to build another nesting or holding block right here. And we want that to match pretty good, because if we just made a flat surface or maybe follow the CAD, it may not nest up well. The part may rock around. So we're going to kind of show you how this is done. So let's start by hiding the base just for a minute. And we're going to roll the part over. And we want to nest it up in this area here. So the first thing we will do is just select the scan data. We'll do that by coming in here, and we'll pick the scan data right up in this area here. And then we're going to go and create a surface. We don't need to model the whole part. We just need some geometry in some of these areas. So we're going to do what's called a mesh fit surface. That's going to basically build a surface, and it's going to try to fit. You can again see that curve. It's going to try to fit those kind of fit the shape there of the part. And we have control on how tight it is. So we've got it pretty tight, but giving it a little bit of room there. So now we have that surface. What we can do, let's bring that base back. And what we're going to do is go into our sketch mode, and we're going to create a sketch, and we'll use this plane. And we'll just come in here now and draw a shape, and we'll just use a line. But basically, we're just going to kind of draw where we want that block, and we're just going to freehand this for this. We're going to draw that block, and it'll fit right there. Okay, so that is down on that base plane. We'll go ahead and take that. And now what we're going to do is we're going to extrude that up, but instead of going blind, we're going to go up to a surface, and we're going to pick that surface there. And you can see it's going to follow that shape. So let's turn off that surface for a minute. Okay. And if you look at that nest, you can see, and you can control this. You can offset the surface a little bit if you wanted it, to have a little bit of a gap or a little bit of play. But that's a very quick way to make a block that would nest up to the surface. And then we'll add our block and put another clamp in like you see here. But this is a great way to quickly build fixtures. In this case, just a simple holding fixture when you either have no CAD data or maybe your part just varies too much from the CAD data. For our final example, we'll also do another fixture design. And in this case, we have an electronics board, as you see here. And again, we do not have CAD for this, and I need to build a simple holding fixture so that we can either add some things to this or do something with this board. Maybe we're repairing it, changing things, and we want something that can hold this board without, damaging it. So we'll walk you through here. And again, we're going to 3D scan this. This time we're going to scan in color. It may not be required, but we're going to scan it in color because there are text and things on there. And depending on the operation, maybe it's important to be able to see things in color or read the text. But again, another example of how we can quickly 3D scan something. Again, even if there's CAD, many times on boards like this, they may change components manufacturer. It may be slightly different. There may have been changes. So there either is no CAD or it's just not up to date. But we'll show you how to design a simple fixture like this as well. So once again, in our reverse engineering software, you can see our fixture. So we've got our scan data in here. Let's hide that for a minute. And you can see it's a very simple fixture. We've just kind of got a ledge here to hold it, and then a little bit of clearance over here to facilitate where this plug is. So very simple to bring the scan data in, do a little bit of offsetting, a little bit of clearance. I mean, you could have some pins in here, whatever you want. But again, the nice thing is we can bring it in color, which can help sometimes identify different components. But just a really quick scan to give us our part, and then we printed a base or designed a base for it as well. But again, another fixture that could be easily 3D printed. So really in a matter of a few hours, you could scan it, design a fixture, and 3D print that fixture. Okay, so in summary, what did we learn? Well, we learned that 3D scanning and probing many times can completely replace fixtures, especially if a part is very rigid. There's really no need to have to design a fixture. Traditionally with CMMs, you almost always use the fixture to get the part in a certain orientation. But with 3D scanners nowadays being so portable and many times non-contact, we can 3D scan or probe a part without really requiring fixtures. Now, 3D scanning and probing is also a great way to validate a fixture, even out on the shop floor. Traditionally, you couldn't take a CMM out on the shop floor, and if you have a very large part, there's just no good way to validate that fixture. Now, as we shown in the example of the welding fixture, we can go right out on the shop floor, establish that datum or Cartesian coordinate system, and fully inspect that fixture, making any adjustments that are necessary and checking it, and also checking it from time to time to make sure it's still good. But we also learned that 3D scanning can be used with fixtures. There are certain types of parts that still need a fixture to hold them in the correct shape so that they can be inspected. And again, that's a great place for scanning and probing to be used, and even on large fixtures out on the shop floor. Also, fixtures may be able to be designed simpler to be used with 3D scanning, and that gap and flush check was a good example. We still need to hold the part, so again, it's in the proper orientation, but instead of doing all those manual gap and flush checks, we now can 3D scan the part and do all of that virtually. So there's no reason to build these very expensive fixtures that then have manual checking processes. We can 3D scan them and have all of that data collected, measure the part, all those measurements, and have it all done electronically in a digital format that can be used for statistical processes or just a historical record of what's going on with that part. And then finally, 3D scanning is a great way to do fixture design. We can 3D scan a part, whether it has CAD data or not. As we talked about many times, the CAD data may not be correct, but then we can build and design fixtures from that 3D scan data. We don't even need to build a complete CAD model. We can work directly off that 3D scan data and build fixtures. So if you want to talk to us more about this, maybe you have a specific type of fixture or project that you would like to discuss with us, you can reach us at 877-845-2700 or send us an email at info@ems3d.com.